Hi everyone, welcome to PRAKASAM tutorials. In this video, I am going to design 3-element Yagi-Uda antenna. So basically, the Yagi-Uda antenna consists of 3 elements. Driven element. So driven element means that is active element, one reflective element and directive elements. So now here I am going to design 3-element Yagi-Uda antenna, and this is the reflector, and this is the driven element or active element, and this is director, 3 elements. And these are the specifications of Yagi-Uda antenna. The length of the reflective element is reflector is 0.55 lambda to 0.58 lambda. The length of the driven element is 0.458 lambda to 0.5 lambda. The length of the director 1 element is 0.45 lambda. Spacing between reflective element and driven element is 0.35 lambda. Spacing between driven element and director element is 0.125 lambda. And length of the second director element is 0.40 lambda. Length of the director 3 element is third director element is 0.35 lambda, and the spacing between the directors is 0.2 lambda. So these are the specifications of Yagi-Uda antenna. So now here I am going to design 3-element Yagi-Uda half-wave dipole antenna at 2.4 GHz. My operating frequency is 2.4 GHz. 2.4 GHz, the wavelength is 125 mm. So I am considering the dipole radius is 0.0625 mm, and the gap values and the dipole element or the driven element gap is 62.375 mm. And calculate the length of the reflector. According to the specification, the reflector element length is 0.56 lambda. Here the wavelength lambda is 125, so 70 mm. The length of the reflector is 70 mm. Now open HFSS software. First create the name of the project. First draw the reflector element. Select the cylinder. Draw the cylinder anywhere in the plane. Give the rename of this cylinder, and the rename is reflector. And type of the material is I am selecting PEC, perfect electric conductor material. And now change the dimensions of the reflector. So now here the dimensions of the reflector. The height of the reflector element is 70 mm. The height of the reflector is 70 mm, and the radius of the dipole is 0.0625 mm, and position. And X position is 0 mm, comma, Y position is 0 mm, comma, Z position is half of the height of the reflector, that is 70 by 2 before representing negative sign, minus 70 by 2 mm. Now click OK button. This is the reflector element, and after that draw the driven element. So first draw the driven element of the upper radiating element. Select the cylinder. Draw the cylinder anywhere in the plane. So give the rename of this cylinder, and this is dipole. and change the type of the material, and the type of the material is PEC. Now change the dimensions of the upper radiating element, and the height, the length is 125 mm and upper radiating element length is lambda by 4. So 125 by 4 is 31 point. Lambda by 4 is, lambda is 125 mm. Lambda by 2, lambda by, so length of the driven element is 0.5 lambda and driven element length is 62.5 mm, and subtracting the gap value, and the dipole radius is 0.0625 and the gap is 0.125 mm, and subtracting the gap value from the length of the driven element, so we get 62.375 mm, and half of its value, is 31.18. So the upper radiating element length is 31.1875. Approximately I am considering 31.19. Height of the upper radiating element is 31.19 mm and the radius is 0.0625 mm, and position and X position is 0 mm and Y position, and this driven element is located along the Y axis, and the spacing between reflective element, this is the reflective element and this is the driven element, and the spacing between reflector and the driven element is 43.75 mm. So the Y position is here 43.75 and Z position is 0.0625. Now click OK button. And this is driven element, upper radiating driven element, and draw the lower radiating element and duplicate of this upper radiating element. Select the upper radiating element, go to right click on the upper radiating element, go to edit, select duplicate around axis and 180 degrees, angle is 180 degree, and select Y, click OK button, and this is the duplicate element around axis, and upper radiating element and lower radiating element. Next, draw the director. Select the cylinder, draw the cylinder anywhere in the plane. Give the rename of the cylinder, and this is director. Change the type of the material PEC. Change the dimensions of the cylinder, and the height of the first directive element is, length of the director one element is 56.25 mm. 56.25 mm, and radius is 0.0625 mm, and position, X position is 0 mm and Y position. That directive element is located on the Y axis, and driven element, reflector element is located on the Z axis. From the spacing between reflector element and the driven element is 43.75 mm, and the spacing between driven element and directive one element is 15.625. 43.75 mm plus 15.625 mm Its value is 59.375 mm. So the Y position is 59.375 mm. And jet position is half of the height of the director element, and the director element height is directive element height is 56.25, and before representing negative sign, so minus 56.25 by 2. Now click OK button. So this is the directive element. This is the reflective element. This is the driven element. This is directive element. After that, assign excitation port. Change the plane YZ plane. Rotate the structure. Arrange in two-dimensional view. Select the rectangular sheet. Draw the rectangular sheet anywhere in the plane. Give the rename of the rectangular sheet is port. And the dimension of the rectangular port is axis is x-axis. Now here the x position is gap. That gap value is dipole radius is 0.0625, and the gap between the driven element is 0.125. 0.0625 into 2, so which is equal to 0.125 mm, and the height is 0.125, and position and x position is 0 mm, and y position and the y position and the spacing between reflector element and driven element spacing is 43.75 mm minus, and subtracting 0.0625, subtracting the that from central position to that y position, 43.75 minus 0.0625. Now here this is the y-axis and this is the central position, and subtracting this value from reflective element to the driven element length is 43.75. So from that 43.75 subtracting this half value. Comma, y position is minus 0.0 minus 0.0625. Now click OK button. This is a port. So now assign excitation port. Select the port, right click on the port, go to assign excitation, select port. So now we are the change the type of the solution. Go to HFSS, select solution type. I am selecting model solution type. Now select the rectangular sheet, right click on the rectangular sheet, go to assign excitation, select lumped port. So draw the new line integration, take the new line integration, draw the new line integration from lower port to the upper port to successfully define new line integration. Click finish button. So this is lumped port excitation. Now coming back to XY plane. This is the reflector element. This is dipole upper radiating and lower radiating. This is the director, and this is lumped port excitation. And after that, assign analysis setup. Now my operating frequency is 2.4 gigahertz and I am selecting maximum number of passes are 12. Click OK button. Selecting the sweep type is fast linear count and starting frequency is 1.2 gigahertz and ending frequency is 3.6 gigahertz and points are I am selecting 101. Now click OK button. Analysis setup is assigned. Now assign the radiation boundary. Now here I am selecting open region. Select the model, right click on the model, create open region, create open region. So my operating frequency is 2.4 gigahertz. Select the radiation. Now click OK button. Select it all. So this is the open region radiation boundary. Now check the design validation. So design is successfully validated. And now start the simulation. Select analyze all. It takes some time simulation. This is successfully completed and after that observe parameter curve, SWR curve. And the S parameter value is at 2.4 gigahertz operating frequency, 12.8 decibel. So now we will change the height of the dipole. At 2.4 gigahertz frequency, the return loss is minus 13.9 decibel. And more VSWR value is at 2.4 gigahertz operating frequency, 1.5. So next observe the 2D radiation pattern and 3D radiation pattern. Okay, 3-element Yagi-Uda antenna. So now here I am selecting families 90 degrees, high values, select gain without decibel. So without decibel this is the radiation pattern and with decibel So this is the radiation pattern. Along this direction it radiates maximum energy. And directivity with decibel. This is the radiation pattern. Directivity without decibel. This is the radiation pattern. Next observe 3D polar plot. So gain without decibel. So the gain value without decibel is 4.51 and with decibel the gain value is 6.54 and directivity with decibel (6.5) and directivity radiation 3D radiation pattern without decibel. So this is a 3D radiation pattern without decibel. This is the gain 3D radiation pattern with decibel and directivity 3D radiation pattern with decibel. This is the directivity 3D radiation pattern without decibel.